Welcome to Jeremy's IT Lab. This is a complete course for the CCNP ENCOR Enterprise Core exam. This course will cover all topics you need to know to pass the ENCOR exam. In the first section of this course, we will look at how packets and frames are forwarded over a network. In this video, we will mainly cover Layer 2 forwarding. Much of the information in this video will be a review of topics you already studied in the CCNA, but we will also cover some new information, so make sure to watch this video. Here's what we'll cover. First, we will briefly review the OSI model. This is, of course, something you should already have learned in your CCNA studies. However, I understand that all of the things you learned in the CCNA aren't necessarily fresh in your mind. So throughout the course, we will include plenty of short review sections to ensure your understanding of the fundamentals is fresh. In such review sections, we will also look at additional details that weren't mentioned in the CCNA course. Next, we will cover collision and broadcast domains. These are also two concepts you should already know from the CCNA, but we will review and clarify them. Then, we will review the Layer 2 forwarding process, how switches use information in the Layer 2 header to forward frames to the correct destination. Finally, we will look at the MAC address table in greater detail than we did in the CCNA course. Note that, although most of the videos in this course will be shorter, this is going to be a fairly long video. However, much of the information in this video is review from the CCNA, so it shouldn't be overwhelming. Okay, let's get started. So, here are the 7 layers of the OSI model, from top to bottom: application, presentation, session, transport, network, data link, and physical. Each of these layers describes different functions necessary to allow computers to communicate over networks. For example, the physical layer defines physical media such as cables, connectors, and radio frequency used for the transmission and reception of raw bits. On the other end, the application layer provides an interface between applications, for example a web browser, and the network, using application layer protocols like HTTP. The OSI model is very helpful because it provides a reference for us to conceptualize and talk about networks. However, as you're probably aware, the actual framework we are using in modern networks is not OSI, but rather TCP/IP. The TCP/IP model shown in the middle of this slide was defined in RFC 1122. It differs from the OSI model in that the upper layers, 5, 6, and 7, are combined into one layer referred to as the application layer, and the data link and physical layers are combined into one layer called the link layer. This is the reference model as defined by RFC 1122. However, there have been many different definitions of these layers over the years. The model I think is most useful for network engineers is this 5-layer model, which splits up the link layer back into 2 layers. I'm including a 7 in brackets here for the application layer, because we often refer to anything above layer 4 as layer 7, rather than layer 5. I think that's a carryover from the OSI model. The main purpose of these conceptual models is to help us think about and talk about networks. However, I don't think it's very useful to be too attached to them. Try Googling for, is ARP layer 2 or layer 3, or is ICMP layer 3 or layer 4. You'll find lots of discussions and arguments online, but personally I don't think worrying about which layer a protocol actually belongs to is very helpful. Some protocols don't necessarily fit neatly into a single layer, and in any case, it's more important to understand the protocols themselves than to fit them into a conceptual model like TCP/IP. With that said, the OSI and TCP/IP models are still great tools to help us understand how networks work. As I mentioned, there have been many different definitions over the years. I took this chart from Wikipedia. All of these here are 5-layer models, and I think a 5-layer model is the best and also the most common way to think about networks these days. Just note that, depending on the author, different names can be used for different layers. For example, layer 3 might be called the internet layer or the network layer. There's no need to learn or memorize these different versions of the TCP/IP suite, but you can check the Wikipedia page if you're interested. Each host on the network runs a network stack consisting of the hardware and software that allows it to communicate over the network. The upper layers prepare some data to send over the network. However, for two devices to actually communicate over the network, we need more than just this. First, a layer 4 header is added to the data. As you know, this is probably a TCP or UDP header. This combination of data and layer 4 header is called a segment. Layer 4 of the device on the left wants to send this segment to layer 4 of the device on the right. However, it's not ready yet. At layer 3, another header is added, with information like source and destination IP addresses to provide routing. This is now called a packet. Again, layer 3 of the left device wants to send this packet to layer 3 of the right device, but it's still not ready yet. At layer 2, a header and trailer are added. Layer 2 allows for addressing within a segment, within a LAN. For example, it allows a host to address this message to its default gateway at layer 2, while still addressing the inside packet to the final destination host at layer 3. As you know, this process of adding headers to the data before sending it over the network is called encapsulation. And the final frame is now sent over the network. The device on the right receives the frame, and at layer 2 checks the info there. For example, it checks if the destination MAC address is its own MAC address. If it is, it opens up the package further to check out layer 3. Note that if the destination MAC address is not its own, or not another MAC address it is interested in, such as the broadcast MAC address, the device would discard the frame before looking at layer 3. No point in looking any further inside. But in this case, it is the correct address, so it checks the layer 3 info such as destination address. Again, it is the receiving host's IP address, so the host knows the packet is destined for it. It then looks inside at the layer 4 information, and if all is good, it removes that too. This process of removing headers and trailers from a received frame is called de-encapsulation. This diagram shows the process. Host A is sending a message to host B, and there are two routers in between them. The application layer of host A wants to communicate with the application layer of host B. For example, maybe host A is trying to use HTTP to retrieve a web page from host B. To facilitate this communication, the lower layers encapsulate the data like this. At layer 2, the message is now a frame. Note that at layer 2, the message is not destined for host B, but rather for the first router. The destination MAC address is the MAC address of the router. The frame is sent over the physical medium and arrives at the router, which notices that the frame is destined for the router's own MAC address. It looks further inside and notices that the layer 3 address is not its own address. So it knows that it has to route the packet, not receive it. It uses its routing table to look up the next hop, uses its ARP table to look up the MAC address of the next hop, and once again encapsulates the packet to make a frame, and send it over the physical medium to the next router. This router goes through the same process as the other router, and once again sends its frame over the physical medium to host B. Host B then proceeds to de-encapsulate the message like this, and then finally the message from host A's application layer has reached host B's application layer. By the way, don't worry if you have forgotten the details of forwarding messages at layer 2 and layer 3. In this video and others, we will review those concepts before moving on to more advanced topics. But I think this diagram gives a good overview of how messages are encapsulated, de-encapsulated, and re-encapsulated as a message travels over a network. The next fundamental topics we will review are collision and broadcast domains. Collision domains first. Early networking technologies like ThinNet, aka 10-base-2, and ThickNet, aka 10-base-5, involved connecting all devices to the same network cable, which was a coaxial cable, as opposed to the current UTP cables we're all used to now. Here's what a ThinNet Ethernet cable looks like, and the connector is known as BNC, again, different than the RJ45 connectors we use today. Here's another picture with a BNC T connector, called T because of the shape. T connectors like this were used to connect devices to the shared cable. Signals sent over the cable are received by all connected devices. Here's a simple illustration. The problem with this is that if two hosts attempt to communicate over the network at the same time, collisions occur. To deal with this, devices use CSMACD, carrier sense multiple access with collision detection. I covered CSMACD in the CCNA. Basically, when devices detect a collision on the cable, each device waits a random period of time before attempting to transmit again. Communications like this, in which devices can both send and receive data, but can't do both at the same time, are called half-duplex. Duplex means traffic can go both ways. A device can both send and receive. Half means that it can only do one at a time. And we use the term collision domain to refer to a network segment where simultaneous data transmissions will collide. So, when devices were connected together using thin-net or thick-net like this, they are all in the same collision domain. Only one device can transmit at a time. Now we'll look at something you'll recognize from CCNA studies. The Ethernet hub is a precursor to the Ethernet switch. It serves a similar purpose as a switch, to connect end hosts to the LAN. But hubs function like multi-port repeaters. A signal received on one port is repeated out of all other ports. Hubs are not layer 2 aware. They do not look at the destination MAC address of the Ethernet header to decide where to forward a frame. They just repeat signals out of all ports. Hubs also have no ability to buffer frames to forward them later, so when a signal is received, it is immediately repeated out of all other ports. This causes problems, because if two devices connected to a hub send data at the same time, the hub will attempt to repeat both signals at the same time, resulting in a collision. The signals that once carried data become a mess that no device can understand. So, like with the previous examples of thin-net and thick-net, all devices connected to a hub are in the same collision domain and must operate in half-duplex, using CSMACD to deal with collisions. Here's a quick example with 4 PCs connected to a hub. These 2 PCs send frames at the same time, and the hub repeats each frame out of its other ports, resulting in collisions. In older, very small networks, hubs were viable, but in modern networks, you'll probably never see a hub, and that's a good thing. Now we have switches, and switches are more intelligent than hubs. They are layer 2 aware. This means that they look at and understand the layer 2 information of a frame, such as the source and destination MAC addresses, and use that information to learn about where devices are connected and forward frames only to the intended destination whenever possible. Another major benefit is that switches have the ability to buffer frames before sending them. This is the reason that, whereas all devices connected to a hub are in the same collision domain, that is not true for switches. If a switch receives 2 broadcast frames at the same time, it will not try to flood both out of a single interface at the same time. One message will be buffered and then transmitted only after the other frame is sent. This means that devices connected to a switch are all in separate collision domains, and therefore devices can operate in full duplex. Devices can send and receive traffic at the same time. There should be no worry of collisions, unless there is something like a hardware fault or misconfiguration causing problems. Here's that same example topology as before, with a switch instead of a hub. 2 PCs send broadcast frames at the same time, and instead of causing collisions, 2 of the interfaces buffer the blue broadcast frame, and only forward it after forwarding the red one. So the switch has broken up the single large collision domain into 4 smaller ones, greatly increasing the efficiency of communications in the LAN. Now let's test your understanding of collision domains. How many collision domains are there in this network? Now this isn't a very well-designed network, but we're just checking if you understand how collision domains work. Remember, every port on a switch is its own collision domain, and every port on a hub is in the same collision domain. Also, every router port is in its own collision domain. Routers operate using layer 3 logic. They don't flood frames. Now, you may have to pause the video to think about what happens when hubs are connected to switches, like in this network. Anyway, let's check the answers. First, this group of ports here are all in the same collision domain. These 2 hubs will flood frames without any buffer, which means that if any 2 devices transmit at the same time, you can expect collisions to occur. I said that all switch ports are in their own collision domain, so why are 2 of this switch's ports in the same collision domain here? It's because they are connected together via hubs, which means they are actually in the same collision domain. This link here, though, is a separate collision domain, because switches are able to break up collision domains. They are more intelligent than hubs. This link between the router and other switch is another collision domain, and the other interfaces of this switch are in their own collision domains too. This switch port here is a unique collision domain too, and this group of links is the final collision domain, all in one collision domain because of the hub connecting them together. So there are a total of 9 collision domains in this network. If you got the answer wrong, don't worry. We'll do another practice question in the quiz after the video. Next, we'll look at broadcast domains. A broadcast domain is a logical division of a network in which all nodes can reach each other by layer 2 broadcast. Another way to put it is a group of devices which will receive a broadcast frame sent by any one of the other devices in that group. As you know, all devices connected to a switch are in the same broadcast domain, because switches flood broadcast frames. If one device sends a broadcast message, all other devices connected to that switch will receive it. Now, VLANs can be used to divide up broadcast domains on a switch. However, we will review VLANs in a different section of the course, so let's not cover them now. As opposed to switches, each router interface is a unique broadcast domain, because routers do not forward layer 2 broadcast messages. So let's practice identifying broadcast domains. How many are there in the network below? Pause the video now if you want to figure it out. Now let's check the answer. Here's one broadcast domain. A broadcast frame sent from any one of the interfaces in this group will reach all of the others, so they are in one broadcast domain. Note that, although I said each interface on a router is a unique broadcast domain, these two are actually in the same broadcast domain because they connect to the same switch. They will receive each other's layer 2 broadcast messages. Here's a second broadcast domain, and this connection between the two routers is a broadcast domain too. They will receive each other's broadcast messages. And finally, this group of devices is also in a single broadcast domain. So, in this network, there are 4 broadcast domains. Collision domains are something we don't really have to think about in modern wired networks thanks to switches, but broadcast domains are definitely something you should be aware of and trying to minimize through the use of VLANs. Now let's move on to the next topic, layer 2 forwarding, which refers to the process switches use to forward frames within a LAN. Switches use information in the layer 2 header to determine where to forward frames. As an aside, although routers operate at layer 3, they are still layer 2 aware, as they must inspect the destination MAC address of frames they receive to check if the frame is destined for the router itself, and then use layer 2 to address frames to the next hop device, or to the final destination host if the router is the last one in the path. Some CCNA students ask why routers need to encapsulate packets within an Ethernet frame, even though routers are supposed to operate at layer 3, so I just wanted to clear that up. Routers use layer 3 information to decide where to forward packets, but that doesn't mean they can ignore layer 2. Back to the topic. There are 4 main message types to be aware of from a layer 2 forwarding perspective. See if you can guess what they are. The first 3 you should already be aware of. Known Unicast frames are forwarded to a specific destination host. Unknown Unicast frames are flooded within the VLAN. Same for broadcast frames. And there is one more message type, Multicast, which by default is flooded as well. I briefly mentioned Multicast from a layer 3 perspective in my CCNA course, but didn't mention Multicast MAC addresses. Later in this course, we will look at Multicast in more detail. Before looking at an example of each message type, let's quickly review how MAC addresses are structured. MAC addresses are 48 bits in length. However, we usually write them in hexadecimal to make them more human-readable, resulting in 12 hex digits. I have an example MAC address here. Why have I colored the first half blue and the second half red? The first half, so the first 24 bits or 6 hex digits, is the OUI, Organizationally Unique Identifier. OUIs are assigned by the IEEE to organizations, and then only that organization is allowed to use that OUI. Large organizations like Cisco will have multiple different OUIs that they assign to their devices. This one here, 0CF5A4, belongs to Cisco. Then, the second half of the MAC address, so the last 24 bits or 6 hex digits, is specific to the NIC, network interface card of the device. For example, this is the MAC address of my switch's Fast Ethernet 01 interface. Other MAC addresses used by my switch, for example the MAC addresses of its other interfaces, or the system MAC address that identifies the switch in spanning tree protocol, would have the same OUI, 0CF5A4, but a different second half of the MAC address. Note that you may see MAC addresses written like this instead, with a hyphen between every other hex digit. For example, if you view the MAC address of a Windows PC with the ipconfig/all command, it will be displayed like this, whereas Cisco displays MAC addresses like the example above. Now let's see how each Layer 2 message type works, and also review how switches dynamically build their MAC address table. In this network, a router and 3 PCs are connected to switch 1, and switch 1's MAC address table is currently empty. R1 sends a unicast frame. The source MAC is R1's MAC, all A's, and the destination is PC1's MAC, all 1's. When the frame arrives at switch 1, what happens first? Switch 1 checks the source MAC of the frame, and because it doesn't have an entry for the MAC address yet, it dynamically learns R1's MAC address. Because switch 1 received a frame from MAC address all A's on interface G00, it knows that it can reach that MAC address on that interface in the future. However, it doesn't know how to reach the destination MAC of the frame, all 1's. That's why this is an unknown unicast frame. So what does switch 1 do with the frame? It floods the frame out of all ports, except the port the frame was received on. Note that if some of these ports were in different VLANs, the frame would not be flooded out of them. But for this example, all ports are in VLAN 1. Now, PC2 and PC3 see that the destination MAC is not their own, so they drop the frame. PC1, on the other hand, is the destination of the frame, so it will receive and process it. Note that, in reality, R1 would probably send a broadcast ARP request to learn PC1's MAC address before sending this unicast message, and in that process, switch 1 would have already learned both R1 and PC1's MAC addresses. I'm just using this example to demonstrate how unknown unicast messages are flooded. Now let's say PC1 sends a response to R1's message. The source MAC of the frame is PC1's, and the destination is R1's. First, switch 1 uses the source MAC address field of the frame to dynamically learn PC1's MAC address and add it to the MAC address table. Then, what does switch 1 do with the frame? Because it already has an entry for the all A's MAC address, it simply forwards the frame out of the appropriate port. Note that switches can only forward frames between ports in the same VLAN. In this case, both are in VLAN 1, so that is no problem. So there's actually no difference between unknown and known unicast frames. They are both frames destined for a single host. The difference is how a switch handles the frame. If a switch doesn't have an entry for the destination in its MAC address table, it floods the frame. If it does have an entry, it forwards it only out of the appropriate port. Next up, broadcast. PC2 sends a broadcast frame, source MAC of all 2's and destination of all F's, which is the broadcast MAC address. When switch 1 receives this frame, it first adds an entry for PC2's MAC address in its MAC address table. Then, what does it do with the frame? As you already know, it will flood it to all ports in the same VLAN, except the port the frame was received on, so it doesn't flood the frame back out of G02. Now let's say PC3 responds to PC2's broadcast message, this time with a unicast frame destined for PC2. First, switch 1 uses the source MAC field of the frame to add an entry for PC3's MAC in the MAC address table. And what does it do next? What kind of frame is this? It's destined for the all 2's MAC address, and switch 1 already has an entry for it in its MAC address table, so it's a known unicast frame. Switch 1 just forwards it out of the appropriate port. Finally, let's look at what a switch does with a multicast frame. Remember, unicast means one-to-one, broadcast means one-to-all, and multicast means one-to-many, but not necessarily all. So what will a switch do with a frame destined for a multicast MAC address like this? By default, Layer 2 multicast messages will be flooded like a broadcast message. You probably have a lot of questions about multicast, but we will cover it in another section of the course, so let's leave it at that for now. Just know that switches flood multicast frames by default. For the last topic, let's take a closer look at the MAC address table and how you can configure it. Here is the output of Show MAC Address Table on my Catalyst 2960 switch. Notice all of these static entries, as indicated with a type of static. I did not statically configure these, but rather they are there by default for various purposes. For example, this first entry, 01000CCC, is a multicast MAC address used for protocols such as CDP, VTP, and DTP. Notice that under the ports column it says CPU. This means when a switch receives a frame with this destination MAC, it should send it to the CPU for processing. Otherwise, it would merely flood the frame, and wouldn't actually look at the information inside the, for example, CDP message. This next one is used for PVST, per VLAN spanning tree, and this one is used for IEEE standard spanning tree protocol. All of the other static entries here have similar purposes. They are there to allow certain protocols to function, because the switch should actually open up and inspect the contents of those protocols' messages. Also, as you may have noticed, the broadcast MAC address is included here, because the contents of a broadcast message may be of interest to the switch, so it should send the frame to the CPU for processing. And at the bottom, there are two dynamic entries, one for my home router and the other for my PC. As you should already be aware, dynamic MAC addresses do not stay in the table permanently. The default aging time of a dynamic MAC address is 300 seconds, so 5 minutes. If a MAC address isn't seen by the switch for 5 minutes, meaning if the switch doesn't receive a frame from that MAC address, its dynamic entry will be removed. However, every time a frame is received from that MAC address, the timer is reset back to 5 minutes. Typically, this 5-minute timer doesn't cause any issues, but you can, if you want, change this setting. The command is MAC address table aging time from global configuration mode. Here, you can configure the aging time in seconds. The minimum is 10 seconds, as indicated by the 10 to 1 million range. Or, as I've highlighted here, you can set it to 0 to disable aging entirely. Dynamic MAC addresses will never be removed from the MAC address table unless you do it manually. I decided to configure it as 0 just for demonstration purposes. Let me repeat, usually there is no reason to actually change the default timer. Note that with the VLAN option of the command, you can actually change the aging time per VLAN. If you look back up at the output of Show MAC Address Table Aging Time, that's why you can see the empty chart with VLAN and aging time columns. I decided to just change the global aging time, not per VLAN. And now, the dynamic MAC address aging time is 0. My switch will keep dynamic MAC addresses in the MAC address table permanently. Another interesting thing is that you can actually disable dynamic MAC address learning entirely. Show MAC address table learning shows us the status of dynamic MAC address learning per VLAN. As you can see, it's enabled on all VLANs by default. These VLANs shown here are the VLANs that currently exist on my switch. To disable learning, use the command no MAC address table learning VLAN, and then the VLAN or VLANs you want to disable it on. For example, I disabled it on VLANs 10, 12, 13, and 14. As you can see, learning has indeed been disabled for MAC addresses in those VLANs. To be honest, this is another configuration you probably won't need to use. Perhaps if an attacker is performing a MAC flooding attack, you could disable MAC address learning on the target VLAN or VLANs, but even in that case, there are probably better options. Now, typically we leave building the MAC address table up to the switch. The dynamic method works fine and is totally hands-off. However, in some cases, you may want to manually configure a MAC address on the switch, like configuring a static route on a router. Here, you can see the two dynamic MAC addresses in my switches table. Note that I'm not displaying the default static MAC addresses here, since they take up too much space. Here's how to configure a static entry in the MAC address table. This is the format of the command: MAC address table static, followed by the MAC address, VLAN, then the VLAN ID, interface, and then the interface ID. Another option instead of specifying the interface is drop. What does this do? It means the switch will drop all traffic for this MAC address. In the next lab video, we'll demonstrate this. So here's the output of show MAC address table after configuring those two static entries. Note that the drop entry I configured is actually my PC's MAC address. I carelessly entered that command while I was connected to the switch via SSH, and then I immediately lost my connection to the switch. The switch was dropping all frames destined for my PC. So I had to get my laptop and connect to the switch's console port and then delete the drop entry so that my PC could connect again. Fortunately, this is just my home network, not a work environment. Although usually, you leave it up to the switch to clear out the MAC address table as necessary as dynamic addresses age out, you can also manually clear all or some of the dynamic MAC addresses in the table. Notice I used the command show MAC address table dynamic to view only dynamic MAC addresses. In this example, there are two. To clear the dynamic MAC addresses, use the command clear MAC address table dynamic. And note that this command is done from privileged exec mode, not global config mode. I used the question mark to view additional options, and note that you can filter by address to remove only a specific MAC address, by interface to only remove MAC addresses learned on a specific interface, or VLAN to only remove MAC addresses learned in a specific VLAN. I just decided to remove all dynamic MAC addresses, and as you can see, show MAC address table dynamic displays nothing. Switches only have a certain amount of memory, and it is possible for a switch to learn so many MAC addresses that it can't learn any more. At the bottom of the show MAC address table output, it does show a MAC address count, 22 in this case, but there's a better way. Show MAC address table count displays the number of dynamic MAC addresses, static MAC addresses, and the total, as well as the total MAC address space available on the switch at the bottom. Note, as I've highlighted, that the total in this command displays 2, whereas above it displays 22. Why is that? It's because all of those static entries that are in the switch by default are not included in this count. That's also why show MAC address table count is showing 0 static addresses, even though you can see plenty of them above. Final point. I just want to show how you can filter the output of the show MAC address table command, as we saw with show MAC address table dynamic a couple slides back. I've highlighted the options you can use to filter the display, such as searching for a specific address with the address option, or filter by interface, VLAN, etc. And if you select an option like dynamic, you can then further filter the output by address, interface, and VLAN. I recommend experimenting with these show commands in the lab to get used to them. Here's a summary of the commands we looked at. If you have access to Cisco devices, whether they are hardware or virtual, I recommend spending some time in the lab, exploring the available commands, and trying them out. In this video, I introduced some commands we didn't cover in the CCNA, but there are still more available, and they might be worth checking out. And that is true not just for this lesson, but for all future lessons too. Labbing is a part of studying that you simply can't skip. And don't just lab what I teach you in these videos. Spend some time experimenting with the other available commands. So, here's what we covered in this video. We started with a review of the OSI model, then collision and broadcast domains. We also reviewed how Layer 2 forwarding is done using MAC addresses, and finally looked at the MAC address table, how to configure it and view it. Much of this video was review, but we also looked at a few new things. Finally, let's move on to the quiz. Here's quiz question 1. How many collision domains are there in the network below? Pause now to think about your answer. Here are all of the collision domains in this network, 8 in total. Fortunately, these days we don't have to worry much about collision domains in wired networks thanks to switches, but they still are important network fundamentals. Let's go to question 2. How many broadcast domains are there in the network below? Pause the video now to think about your answer. Here are the broadcast domains in this network, 7 in total. To help you visualize it, These arrows show some example broadcast messages and which devices they would reach, indicating the broadcast domains. Remember, a broadcast domain is the group of devices that would receive a broadcast message sent by one of the group's members. Okay, let's go to question 3. Which of the following Ethernet header fields does a switch use to make a forwarding decision? Pause the video now to think about your answer. Okay, the answer is B, destination MAC address. In Layer 2 forwarding, switches don't look at Layer 3 information, so C and D can be ruled out because they mention IP addresses. Plus, the question mentions the Ethernet header, and IP addresses are not part of the Ethernet header. As for A, the source MAC address field of Ethernet frames is used to build the switch's MAC address table, but when it comes to actually forwarding a frame, it looks at the destination MAC address field and makes a forwarding decision. So B is the correct answer. Let's go to question 4. Which of the following message types is not flooded by a switch? Pause the video now to think about your answer. Okay, the answer is D, known unicast. Broadcast messages are always flooded. Multicast messages are flooded by default, and unknown unicast messages are flooded because the switch doesn't yet know the correct port to forward the frame out of. Known unicast messages are not flooded, because the switch already has an entry for the destination in its MAC address table, so it can forward the frame out of the appropriate port. Let's go to question 5. Which of the following commands can be used to disable dynamic MAC address aging? Pause the video now to think about your answer. Okay, the answer is B, MAC address table aging time 0. C and D are not real commands. And what about A? Actually, A could be used to return the aging time setting to default. For example, if you used the command MAC address table aging time 0 to disable MAC address aging, command A, no MAC address table aging time, would remove that command and return it to the default setting of 300 seconds. Okay, that's all for the quiz and today's video. Before finishing this video, let me thank my JCNP level channel members. To become a member, please click the Join button under the video. Thanks to Jonathan Makara, Boson Software, Velva Jacom, George Streeter, Funny Dart, Nasir Chowdhury, Gustavo BR, Gerard Baker, Marcel Lord, Pavel M., Dragos Hernia, Meir Salman, Mason Anderson, Vitaus194, Gina Lindley, Nehemia Bold 1C1U, Mark Jackson, Michael Carroll, Gerald Guillaume, Gabriel Braga, Renan Moraes, Hector Hernandez, Ali Polat, Maratuba, R. Nelson, Roji Kuriakos, Roscoe Roy Gamer YT, Owad, Arpad Konives, 5 Feet, Daniel Brown, Emiliano Correa, Leonardo Souza, Tricky Mickey 123456, Scott Thompson, Jose Alvarez, Kevin Hayes, ES, William Rosario, and Hussein Yavuz. Sorry if I pronounced your name incorrectly, but thank you so much for your support. Thanks to you and my other supporters, I am able to make these videos and release them for free on YouTube, so I really appreciate the support. Another great way to support the channel is to like the video, leave a comment, subscribe, and most importantly, share this video with others. So if this video was helpful, I'd appreciate it if you did any of those. Thanks for watching.